So what is kinetics? In physics, we talk about kinetics as movement of objects. In chemistry, we're more interested in rates of change or rates of chemical reactions. And what are the factors that affect the rates of reaction? Well, obviously there's temperature, which is the temperature of the whole system. There's the concentration of the reactants, there's the catalyst, there's also surface area, whether a reactant is finely divided particles or in big lumps. This can also be classed as the nature of the reactant. So the phase, such as the gas versus the liquid versus the solid, or the reactivity, such as a strong acid versus a weak acid, or a reactive metal versus a non-reactive metal. But why do these factors affect reaction rates? Well, it has to do with collision theory. Particles have to collide with enough energy and in the correct orientation in order for a reaction to proceed. We can even define an equation that shows how the number of molecules reacting per unit volume per unit time, which is your rate, is dependent on the number of collisions per unit volume per unit time, i.e. the rate of collisions, times the fraction of collisions having an energy greater than EA, which is your activation energy, times the fraction of collisions that are actually in the right orientation. So how does collision theory explain how these factors affect the rates of reaction? Let's try an example reaction. Hydrogen peroxide decomposing to form oxygen and hydrogen. To start with, we look at temperature. An increase in temperature always increases the rate of reaction. This is because it increases the average energy of the particles, which means that more particles have energies above the activation energy and are able to react. In this case, an increase in temperature increases the rate of decomposition of hydrogen peroxide. What is this activation energy? Well, in the enthalpy diagrams, remember enthalpy is a measure of the energy of a system. We have the reactants and the products and the enthalpy of the reaction, like so. But in reality, the reactants must have a certain minimum energy for the reaction to proceed. This is represented on the diagram by this hump. For an exothermic reaction, the energy is small. But for an endothermic reaction, this energy is quite large, which is why they don't occur spontaneously. How does temperature affect this? Well, remember that the enthalpy of the reactions is the energy of the system. If the temperature is increased, this energy is higher, and therefore the activation energy is smaller. For an exothermic reaction, the activation energy is this hump in the curve. For an endothermic reaction, the hump is not necessarily larger, but you'll see that it also contains the enthalpy of the reaction. It's actually easier to visualize this using a Maxwell-Boltzmann distribution. A Maxwell-Boltzmann distribution shows the distribution of kinetic energy of particles in a gaseous system. The average kinetic energy is defined as the temperature of the system. We can use them to explain other phases, though, even though they don't really apply. The distribution looks like this for a specific temperature. Some of the particles have energies greater than the activation energy and hence will react. However, the majority do not. An increase in the temperature shifts the distribution like this, and this means more particles have energy greater than the activation energy and the reaction proceeds at a faster rate. In practice, this means that the peroxide will decompose faster at room temperature than in the fridge. One of the reasons why we keep it in the fridge. But how does a catalyst affect the reaction? Well, a catalyst has a similar effect on the distribution, but for a different reason. It provides a different pathway for the reaction to occur. On the distribution, it looks like a lowering of the activation energy, but this is not really true. It's simply providing a different pathway with a different activation energy that just happens to be lower than the first. So more particles will have energies above this activation energy on the distribution. On the enthalpy diagram, this looks like a mountain, which is the original activation energy, with a tunnel through the middle, which is the new activation energy. Lowering the activation energy is really just allowing a different pathway for the reaction to proceed. Some particles will still travel over the mountain, but the rest will take the easy tunnel route, which will increase rate of reaction. In biology, we use enzymes as catalysts for that peroxide reaction, but they're sometimes affected by temperature. So what do we use in chemistry? For this reaction, we use manganese dioxide. It provides an alternative surface for the reaction to occur, but it's not used up in the reaction, and it's also not affected by temperature, unlike enzyme catalysts. So catalysts and temperature are really changing the energy of the system, but what does concentration do? Concentration is easy to explain. If you have more particles, then there's more chance of a collision, and there's more chance of a successful collision, i.e. with the correct orientation, and they'll collide more often. So if we use a 30% peroxide solution, it will react much faster than a 3% solution, a bit like bumping into someone special at a party. It's much easier than when there are more people. You can extend the analogy of the party for gaseous reactions to include things like pressure and volume. The pressure would increase if the volume decreased, which would be like increasing the concentration. It would be like having the party in a smaller room. The nature of the reactant is the next factor, and it covers several different properties. First, the phase, be it solid or liquid or gas. Obviously, a gas has inherently more energy than a solid, and hence is more likely to react and have more frequent collisions. The nature can also cover the type of reactant, a strong acid versus a weak acid, for example. A strong acid will react faster than a weak acid, although this is actually due to the concentration of hydronium ions in the solution, so it could be classed as a concentration effect. There is also surface area. The reason small particles react faster than large particles is actually due to the surface area versus the volume ratio of the particles. If we have the same mass but smaller particles, they'll have a larger surface area, which means more surface area is available for collisions to occur. In heterogeneous reactions, such as those that occur in solid, liquid and solid gas phases, which is really common in biology, the other reactant has to collide with the surface for the reaction to occur. More surface area means more sites for reactions to react, and hence the rate of reaction is increased. In the peroxide reaction, finely divided manganese dioxide, or catalase enzyme, would be better than a lump of manganese dioxide. How do we measure rates of reaction, and what do these rates look like in a graph? We often measure the rate of reaction by measuring the change in the mass, or volume of a system, the change in concentration of the reactants or products, or the amount of gas evolved, like in our peroxide reaction, over time. All these changes are a way of measuring the rate of reaction. So if we plot the change in reactant over time, we see that initially there's a lot of reactant, but the amount decreases over time as the reaction proceeds, and the concentration of the reactant is diminished. However, this concentration is stable. If the reaction proceeds to completion, there'll be no more reactant, but more often it reaches an equilibrium where the forward and backward reaction rates are the same. For the product, the opposite occurs. Initially, the amount of product is zero, but this increases over time until the reaction is completed or an equilibrium is established. But different graphs can show different proportions of reactants or products, but still the same rate of reaction. How does that work? Well, the rate of reaction over time can be represented by this graph, rather than concentration versus time, and both those previous graphs can be represented by the same rate graph. Initially, the rate of the forward reaction is fast, and this rate slows down as the concentration of reactants decreases. In contrast, the rate of the reverse reaction is initially slow because there's no products for the reverse reaction to occur, but as the amount of products increases, this backward rate also increases. At the end point, the rate of the forward and the backward reactions are the same, which is equilibrium. How do these factors that affect reaction rates change these graphs? This is a good question. So, temperature can increase the rate of reaction. The reactant decreases faster and the product increases faster. And the concentration time graph looks more like this. And the rate graph will look more like this. Surface area would have the same effect, and the graphs would look similar. And concentration would change the concentration time graph as well as the rate graph, so that the reaction rate is faster and the position of the final concentration of products and reactants will also be different. A catalyst would just increase the rate versus time graph. A catalyst would not change the amount of products, just how fast they were produced. So the reaction occurs until it either finishes, the reactants are used up, or is at equilibrium. But the amount of product, or the equilibrium position, is only dependent on the initial amount of reactant, its concentration, and the temperature of the system.